Hi everyone, we are still discussing introductory topics for the purpose of preparing Calculus 1. In this section, called section 11.2, we will look at operations on functions. This addendum to section 11 will cover operations that involve two or more functions. We're going to start off with addition. So labeling a function f plus g that is acting on some value x is equivalent to calculating f on x and g on x individually. For example, if the functions that we are considering are x squared plus 5x, and in the case of g of x, ln of x minus e to the power x, then the function formed of the sum of f and g would be obtained by adding the individual functions that we started off with. X squared plus 5x plus ln of x minus e to the x. The need for parentheses is not necessary, and we'll just simply remove them. So we create a new function whose name is actually f plus g, but it is the result of f and g's addition individually. Similarly, when it comes to subtraction, the function f minus g is obtained by subtracting f's result on x and g's application to x. For instance, x root of x minus 4 over x is what we've labeled as f, and the operation tan of x minus the absolute value of x has been defined as function g of x. The function f minus g is obtained by subtracting function g from function f. In this case, the signs obviously distribute to both the tan and the minus absolute value of x, and therefore creates a new function. So root x minus 4 over x minus tan x plus absolute value of x is actually the rule for function f minus g applied to x. In the exact same way, the product of f with g is obtained by multiplying f of x with g of x. So for instance, if f of x stands for function cos of x, and if we label tan of x as g of x, then the product of f with g calculated at x is the result of f at x multiplied with the result of g at x. So cos of x times tan of x. For those of you who've seen all sorts of identities that relate to trig functions, then you're more than welcome to use them. For instance, tan of x is defined as sine over cos. And yes, you would be allowed to cancel the cosines, as we saw in our sections on fractions, but this is only allowed in situations where cos of x is not 0, because tan of x was not defined at those moments originally. The function that results from the division of f divided by g, calculated at x, is obtained by dividing f of x by g of x. So if f of x is x squared minus 1 and g of x is 2x minus 2, then what we call the quotient of f with g is obtained by doing the division of f of x by g of x. Once again, if you see any simplifications that can take place due to factoring, that's fine. So in this case, we have common x minus 1 factors at the numerator and denominator, but we do have to impose a restriction, which is that x minus 1 is not 0. Composition means inserting a function's result into the other. More specifically, f compounded with g, or compounded to g, calculated at x, is obtained by using g of x as the argument in f. For example, if f of x is defined as e to the x times x plus 1 squared, and if g of x is defined as the root of x minus 1, then the composition of f with g calculated at x means evaluating function f with g of x as its argument. So in other words, we will replace g of x by what it stands for. It stands for the expression root x minus 1. And root x minus 1 now acts as the variable that is applied to function f. So if you recall in section 11, we said that x is a placeholder and can be replaced by more elaborate expressions than just numbers or just x's or just variables. In this case, we have an entire expression called root x minus 1, which is where function f is evaluated. So you'll notice that everywhere we used to see an x in the rule defined by a function f, we now find a root of x minus 1. We can then proceed to doing simplifications if we notice any of them, and certainly here a minus 1 plus 1 combination, and rooting x and squaring it reduces also to x. Now, I haven't talked about considerations for domain, but obviously we have to make sure that we use values of x where g is defined in the first place, and then where f is defined for values of g of x. So in this case, for instance, function g only exists for non-negative values of x, and that would constitute the domain for the composition as well. Now, it's important to notice that the order of composition is very important as well. For example, if we reuse the same two functions we had in our previous example, so functions f and g, if we were interested this time in finding the composition of g on f of x, then f of x would become the argument that is to be inserted into function g. F of x stands for e to the x times x plus 1 squared. This becomes the placeholder that replaces what used to be x in function g. So again, you have to think of this entire red expression as being the x that we are actually using in function g. So rather than rooting x, as g prescribed in the first place, we are now rooting the entire result of f of x. And that's followed by a minus 1. Properties we've seen for roots allow us to root e to the x and x plus 1 squared individually as they're both positive. And if you want to simplify some more, remember that rooting or doing the square root of a squared expression requires that we maintain absolute values to guarantee a positive outcome is obtained. Now, this composition is actually defined for all x because this time f of x is, or function f, is the first operation to take place on x. E to the x and x plus 1 squared are defined for all x's. By the time we've calculated the result, since e to the x and x plus 1 squared are both positive, we are guaranteed that rooting the result of f of x will be defined. Quick note on inverse functions. F and g are mutual inverses when their composition creates a result of x. So composing g with f of x or f on g of x should give x as the result. In other words, whatever f has done to x, g has undone it. And likewise, whatever effect g had on x, f will undo it as well, hence the name inverse. For instance, if f is defined as 2 over x plus 1, and g is defined as 2 over x minus 1, we can show that these are mutual inverses, since computing g of x and using it as the argument within f, we'll notice that the outcome is x. Restrictions force us to avoid using an x of 1, otherwise g of x would be undefined. Along the way, we've used properties of fractions, and we've simplified whatever we could. Likewise, if we compose g on f of x, so this time we have to find the result of f of x first, 2 over x plus 1, which we are inserting as the argument of g. So what used to be x in function g is now replaced by 2 over x plus 1. And this will simplify to x as well. This time we have to avoid x's becoming 0 or being 0, because otherwise f of x would be undefined initially.